We are recording. All right. So in the book is chapter 1, section 1. And the overall big picture here is problem solving. So that is what we're going to be building to. All right. So where we're going to start is first just looking at two types of reasoning. When I talk about reasoning, really what I'm after is how we draw a conclusion based on a set of what we'll call premises. And there's two main forms of reasoning. We're going to go over each of those right now. So the first type we're going to refer to as inductive. All right. So inductive reasoning. It's characterized by drawing a general conclusion from repeated observations of specific examples. Now, the conclusion in and of itself may or may not be true. So that is, there's no way to formally prove your conclusion to be true. It may be true. A simple example of this would be something of this nature. It has snowed for the past 4 days. Therefore, tomorrow it's going to snow. So my repeated observation of a specific example was each day, for 4 consecutive days it snowed. And so I reached a general conclusion that tomorrow it's going to snow. Maybe it does, maybe it doesn't. But that is the kind of the nature of inductive reasoning. Now, I'm going to pull up something here. I had it up and then I switched it out. Okay. Now, a couple other notes. So, in inductive conclusion can be analyzed spelled that. Only in terms of its strength. So that is, how many repeated observations have I made? If I've made 100, they're all doing the same thing, then I can say, my conclusion, that is very strong. Still doesn't mean it's true, but that's it. Again, there's no way I can actually prove the conclusion true, right? At best, if it's a strong argument, I can say it's probably true, but that is it. And then in terms of, and I think I'll put this down after I look at the other type of reasoning. But I'll write it down here in a minute when I compare the two. But general to specific in terms of inductive, I'm drawing a general conclusion based on specific examples. All right. And I'm going to flip the page. If I ever flip a page and you miss something or we're still writing, just holler at me or chat in, and I can always turn the page back. So if I don't hear any objections, I'll turn the page. And I want to look at deductive reasoning. All right, so deductive reasoning is characterized by applying general principles to specific examples. Okay, so another way to kind of think of this is I have a set of premises I'm looking at, and I apply generally held rules, laws, etc., to draw a specific conclusion. And so where inductive reasoning is moving from specific premises to a general conclusion, deductive is moving from a general premises to a specific conclusion. Okay. All right. Now, in terms of analyzing your deductive reasoning, it can be analyzed in terms of its validity and soundness. All right. Now, so those two things. So your reasoning deductively, it is valid if the conclusion necessarily follows from the premises. I am on a roll. Cannot spell today. necessarily, if the conclusion necessarily follows from its premises. So whatever rules, laws, etc. you are using to draw your conclusion, if your conclusion logically follows from that initial set of premises, we say that this deductive argument is valid. Now, here's the thing about deductive reasoning. Whatever rules, laws, etc. you're using to then draw your conclusion, that conclusion may absolutely be wrong. I mean, false. However, it's still valid because it logically follows from that set of premises. It all just depends upon the rules that you are using. So as an example, and I think I've mentioned this in class before, I don't argue politics or whatnot, but I will vehemently argue that the world is not flat. Right. So, and there are those out there that believe such. So, but no, the world is not flat. We live on a sphere. But once upon a time, that was the general belief. So, so if you're using that as your premise, well, again, your conclusion is going to be blatantly wrong, but logically it follows. So that's what makes an argument valid. So whatever premises you're using, you can then logically move to the conclusion. You've got a valid argument. Now, it is sound if it is valid. So if your conclusion does not logically follow from your premises, you can't be sound because you're not valid. So again, to be sound, you have to first go through that first check, and that is the argument valid? Right. So it's sound if it is valid, and its premises are true. Spell. All right. Its premises are true. So now, if you have a deductive argument that is both valid and sound, it's valid because your conclusion logically follows from your premises, and those premises are true. So your conclusion, therefore, is going to be true. So validity and soundness. All right, so those are our two basic types of reasoning. So in mathematics, in terms of when we look at building a mathematical system and we write these conditional statements, we call theorems, and then we write deductive arguments to prove them. But we also, in order to even generate the idea of a theorem, we're initially using inductive reasoning and watching repeated observations of patterns. Then we move to deductive reasoning to try and logically prove said theorems. Now the book doesn't throw this in there, but I would throw one more type of reasoning in there in addition to these two, and that's what I would call intuition. Intuition, there is no basis, there is no repeated observations you're looking at, and you're not applying general principles to specific examples either. Another way to say intuition, gut feeling. I have no basis to judge my conclusion other than I just have a feeling this is how it should be. And that can, is still important in terms of just even generating a new idea to start thinking about. All right. So I would definitely throw that into the mix. All right. So on the homework, A lot of these are very short kinds of problems, but it starts out with the first 8 or so problems just dealing with giving you an example and then saying, am I using inductive or deductive reasoning? And so I'm just looking at number 1 as an example. So number 1 from the homework. Simple question. The next number in the pattern is, and I've got 8, 12, 16, 20. And then it says, all right, so the next number in this pattern is 28. All right. So, which seems reasonable, but again, what's important here is this an example. If I say the next number in this number pattern is 28, am I using inductive or deductive reasoning? And the answer here is inductive. I use a repeated series of observations that it would appear that what I keep increasing by 4. Oh, and of course that didn't make sense unless I put 24 there. Apologize, I missed a number there, but it's increasing by 4. But it was, again, I'm looking at that repeated series of examples to draw that general conclusion that the next number is 28. Now, when you are given your choices, you're given 4. 2 of them say inductive, 2 of them say deductive. So first, just okay, it's inductive. Now I've got 2 to choose from. And what they do is they mix up the definition of inductive and deductive. And so you want to choose, in this case, the reasoning is inductive because a general conclusion is being made from repeated observation of specific examples. The other selection of inductive actually has the definition of deductive. So let's find one that is deductive. So looking at number 2, what it does is say to find the perimeter P of a square with side length S, I can use the formula P equals 4S. So if a perimeter of a square with side length of 7 would have a perimeter of 4 times 7 or 28 inches. So in this case, again, I'm looking at general principles in this case that if I have a square, all 4 sides have the same length, and the perimeter would be 4 times that side length, because you're just adding up all the sides, lengths of every side. And then it moves to a specific example of, well, then if you had a side length of 7, then your perimeter would be 4 times 7 or 28. And I think it uses inches as the units. But the reasoning is deductive. Any questions on those 2? Okay. Any questions? All right. All right. So Now, once you get past, it looks like 1 through 9 of the homework. You're just going to have a series of questions that deal with looking at number patterns, pattern recognition, and predicting. So you're really using inductive reasoning for all these. Doesn't ask for the type of reasoning, just wants you to predict the next number. So as an example, I'm looking at number 10, and it's just going to say, okay, you've got a list of numbers 10, 12, 14, 16, 18. What's the most next probable number? And I would say 20 because it's increasing by 2 every time. But there are various number patterns that so you have to, for each one of these, I'm just jumped up to number 13. It's a question of finding that pattern. That's really what you're after here. So I'm looking at 13. I've got 4, 5, 9, 14, 23, 37. And then it wants you to put in, what do you think the next most probable number is? So this one I'll throw open to the group. You can verbally say what you think the answer is, or type it in chat.
60.
And I hear 60. Someone chatted that in. And correct on both. So both of you, there were 2 people who answered 60. And it is 60. And the deal is what I'm looking at, it's kind of what Fibonacci. I add up what the previous 2 terms to get the next term. 4 plus 5 is 9, 5 plus 9 is 14, 9 plus 14 is 23. And again, we're using inductive reasoning here, a series of repeated examples to draw. The next one is for sure 60, or more than likely sure. And then once you get up towards around 18, 19, it's actually going to give you kind of a series of crazy equations and ask you to predict what is going to happen next. So let's see here, looking. All right, this will take a second to write down. It's worth looking at. So I'm actually looking at number 19. So first I got to write down all right, so basically we're saying 333 times 333,667 equals 111,111,1111. And we could take a calculator and verify that. But then it gives you a next line. 666 times same number. Numbers are crazy things. Right, we could get a calculator and verify that. Gives you a third line, 999 times that same number, 333,667. And we would probably inductively predict that it's going to be this. Okay. And it gives you a fourth line. And times, you guessed it. And you would probably guess or draw a conclusion inductively that this is going to be this. So what it wants you to do is basically figure out what you're going to put here times this, and then what you're going to put here. All right. So same deal. Let's go with this one first. Probably the easier of the two. What digit would it appear to have to be?
Bunch of fives.
A bunch of fives. So 555 million, and I draw 7. But all fives across the board. Should seem like that is what it should be. All right, now I had grabbed my calculator on the other number on the left side here. What do you think this number should be?
$16.65.
That is exactly it. Thank you very much. 1665. And how did I arrive at 1665? Or how did you arrive at it? What are you adding each time? So how did you come up with this number? What was the pattern?
You add 333.
That's it. You keep adding 333. So that's boom, boom, boom. And then 999 plus 333 gets you to 1332, and then 1332 plus 333, but add 1332 plus 333 is 1,665. And it would appear now we could keep going. And again, we're reasoning inductively. It's not a formal inductive proof or deductive proof, but it definitely seems very reasonable that this pattern continues on. I could keep on generating more and more equations using this kind of pattern. And so again, starting with 18, 19, 20 is kind of the same vein. 21, 22, 23. Then we hit 24. Now, I couldn't remember in my Thursday class hadn't seen this, my Tuesday, Thursday class, but I am fairly confident. I knew I had done it in one of the two. And I think we have done this one before. So I'm going to turn the page. Do you remember working this one out first day of class? Young 6-year-old boy back in about the 17th century. First grade teacher gave them a problem to work on to keep them busy. You guys remember doing this?
Yes.
Okay. So there's actually a couple problems dealing with this very thing, and it talks about the story. That young kid, anyway, incidentally, the sum was 5,050 in this case. And again, 6 years of age, I'm not figuring that out, not in 30 seconds, and probably not if you gave me all day at 6 years of age. The kid's last name was Gauss. It was Carl Friedrich Gauss, who lived from 1777 to 1855, and ended up, and still to today is referred to as the world's greatest mathematician that ever lived. There's not an area of mathematics he didn't touch. But what he figured out, again, by pattern, was instead of just directly going 1 + 2 is 3 and 3 + 3 is 6 and 6 + 4 is 10, that I can add in any order I want. And I made the observation that, well, 1 + 100 is 101. And 2 + 99 is 101. And 3 + 98 is 101. So that I'm just pairing them up like this, and then realizing, well, there would be 50 pairs of 101s. So the sum would have to be 101 times 50, which is 5,050. Now, so there's several problems that actually ask you, it explains all this, talks about Gauss a little bit, and then asks for different sums, but using that same method. Now I'll go ahead and throw this out to you. When Gauss was about 20, he figured out that if I add up the counting numbers starting at 1, consecutive counting numbers starting at 1, up to any counting number in, I could take that last number and put it in this formula, and that will be the sum. And, prove that deductively, that this formula always works. So as an example, if I would just figure up this sum, then n would be 100. And if I plug that in there, well, 50 goes into 100 twice. Or, I don't know why I wrote a 50 down there. It's a 2 down there. 2 goes into 50, or 2 goes into 150 times, and 100 plus 1 is 101, and I'm right back to 50 times 101. Sum. Now, this is something that will be the next class, which again for you guys, and you're just going to get the video recording of the 1.2 material, but we're going to be looking at summing formulas, 3 of them, one of which is this one, and then there'll be a couple others. And so this is a little bit of a preview to that. This n isn't necessarily just the last number of the sum. What n is actually is the actual number of numbers being added up. It's referred to as the ordinal number. So it's simply the number of things that we're adding, that we're going to add up. We're going to look at a summing formula for adding up consecutive odd numbers. So if I added up consecutive odd numbers starting at 1, say I just added up 1 + 3 + 5 + 7. The last number in the sum is 7, but I didn't add up 7 things. I actually added up 4 numbers. and N would be 4 in that particular case. So that's just a preview again of next time. But the problems here dealing with Gauss want you to use Gauss's method. And like I'm just looking at the first problem, it goes 1 + 2 + 3 plus, and then up to, in this case, it says 400. But I could still use that same pairing idea. But I've actually even given you the formula that you could use to find the sum. So you've got that now. But you could say 1 + 400 is 401. And 2 + what, 399 is what, 401. And 3 + 398 is still 401. And then it comes down to how many pairs of 401 in this case do I have? And how many would I have?
200.
200. All right. Anyone want to multiply that up for me? What is 401 times 200?
80,200.
200.
All right. So 80 what?
1,200.
80,200. Likes it. Now, again, that would be using that method of 6-year-old Mr. Gauss. If you put it in that formula, notice it's still going to work out to be 200 times 401, which is still 80,200. There are a couple more like that. Then there's one that you're not going to be able to use this formula that I gave you, because this formula, n times n + 1/2, is dependent upon your sum starting at 1. So on number 27, you're going to have to modify the 6-year-old Gauss approach to do it. I'll certainly, a week from today, answer any questions if you get stuck on that one. The very last problem, I like to do this one, and I like being able to just look at it with you guys not being able to. And it's a number pattern. This is the last problem in the homework. Here's a number pattern: 12, 1, 1, 1, 2, 1, 3. All right. 2 questions. First question is, what do you think is the next most probable number?
Maybe 1.
All right. Did I hear 1? And that, to me, if I had to say what is the next most probable number, I would say 1. But, and we're using inductive reasoning, I would say we're moderately strong on strength here. Because my next question is why? What would lock it in?
Just because there's more ones than anything else.
Yeah, well, this seems a little confusing. I got those 3 1s all together, right? But then it seems to be alternating. So when you actually look at the problem, it gives you a hint. And to me, it gives you such a hint that you just immediately see why you have this. It's a little bit too much of a hint. I'm just going to first, can anyone think of something? And I would say everybody has seen this, and this is a little bit of a hint, heard this, that creates this number pattern. Every single one of you have seen and heard what I'm thinking of that would create this number pattern.
some kind of like binary code.
Okay. I like because you see all the ones. Not a binary code though. Not a bad guess. Now I'm reaching for hints here. Something probably every house has one of at least, but not necessarily with the sound. We honestly, in our house here, I probably have, I'm just thinking right now, I've got one in the living room. I've got one in the bathroom. I've got one in the kitchen.
Phone?
A phone? Excellent guess, but nope. Predates phones. Somebody chatted something in here. Let's see. Aha. Okay, someone just texted directly to me and got it. So I won't say if they, since they sent it to me privately. They know who they are. They answer clock. Okay, so that's what I'm getting back to when I said see and what hear. So not all clocks you're going to hear, but what kind of clock? Definitely a grandfather clock. Any clock with a Westminster, what's called the Westminster chime. So we have one now on our campus, right there in the middle, right in front of the college, in the big grassy area out front. There's a big clock tower, and most college campuses have one of these. But what does a grandfather clock or a clock with a Westminster chime? How many times does it chime on the hour? That, whatever that hour is, right? So at 12 o'clock, it's going to chime what? 12 times. But on the half hour, it only chimes what? Once. So at 12:30, chimes once. 1 o'clock, it chimes once. 1:30, chimes once. And then you get to 2 o'clock, 1, 2:30, 3 o'clock, 3:30. So when you do this problem, it's going to be real easy to knock this one out for sure. The last problem. The hint they give you is think about a clock with chimes, and boom, you immediately get it. They didn't used to do that, which definitely made you think a little bit more, I think. So, and that is it. So I'm putting due date on the homework, which this homework is going to actually be, it should order wise, when you hit assignments, it's actually going to be before the chapter 9 stuff. Again, just because of the way I have things ordered. And, but I put a due date of the 20th. Oh, I guess it's a due date of the 20th, but that's Monday. So I'm going to yeah. So I'll leave the due date there of the 20th, which is Monday, for a class on Monday. Again, just for pacing. On Thursday, again, I will send video link to that will cover the material that's assigned in 1.2. Now, I may not be able to get through, and it's usual that I don't get through everything in 1.2. There's a good bit in there. I'm going to be looking at specific summing formulas, at different types of number sequences, geometric, arithmetic, looking at what's called a method of successive differences. And then there's a whole series of sequences called figure numbers. Typically, I don't get to figure numbers in that one class session. So how much ever I get covered on tomorrow, I will certainly email everybody and say, so if I don't cover everything, I'll say on 1.2, you're responsible for these problems only. And then, so I'll send that video link and then I will sign 1.2, but the due date will be the 22nd, which would be a week from today. So does everybody understand how we're going to proceed? All right, so I have assigned 1.1. And again, I will send the video link for 1.2 and whatever I can get covered there. And then a week from today, I'll take questions on both 1.1 and 1.2, how much ever I have assigned. So be definitely looking for emails from me tomorrow. So are there any other questions from any of you guys? Are we all good? All right, gang. Be safe out there, and I will see you live a week from today on the 22nd. All right, and as always, if you have questions or comments, concerns, whatever, shoot me an email. So I will get back to you. All right, gang. Have a great day.